So this is asking us to just estimate really a force. So the idea is that we have some kind of a house, I know, box structure, not the wisest choice for a roof, but that's okay. And we have wind above, outside, in speeds of about 100 miles an hour, 45 meters per second. And the question is, what's the force due to the Bernoulli equation on a roof with this area? And so as we look at this, if we just compare, say, the pressure right here, right on the inside under the roof, compared to the pressure here, we'd say they're essentially at the same height. Then we could say pressure 2 plus, because there's moving air, 1/2 rho squared, plus rho GH, we'll call the height basically 0. So we'll set this as our H equals 0. Must be equal to pressure 1 on the inside plus 1/2 rho V squared, but that's going to be 0 because the air is still inside as long as windows aren't open, plus rho GH, also 0. So that gives us sort of our setup as we go. And so we can find certainly this quantity because we've got the density of the air times, because that's the fluid that's moving, times the speed. So we already have that. And what we want to know is what's the force? Well, the force would be due to the difference in pressures, right? So we would have this pressure 1 pointing up, pressure 2 pointing up or down, depending. But in this case, pressure 2 is less. So this is a smaller pressure. Sorry, not the pressure pointing, the force. So smaller pressure, larger pressure. And so the force that we would have up, the force up, would be the difference in these two pressures, pressure 1 minus pressure 2, all over, all of that force up over area would be this pressure difference. So we could say that force up is equal to pressure 1 minus pressure 2 times the area. So force up is equal to pressure 1 minus pressure 2, which we can get from solving Bernoulli's equation, right? I'm going to do it up here. So I'm going to say 1/2 rho V squared is equal to, I'm going to move this, subtract it from both sides, that'll be P1 minus P2. There's my pressure difference, so that's just 1/2 rho V squared times the area. So the force, the upward force, is equal to now 1/2 rho. In this case, that's 1.14 kilograms per meters cubed times our V, 45 meters per second squared, times our area, which is 220 square meters. So that goes away. So I've got kilograms meters squared per second squared. Meters squared, sorry. So that gives me kilograms meters per second squared. And so the force up, I calculated to be about 254 times 10 to the third newtons, which seems like an enormous number. But how do we get a hold of that number? If we have a roof that has an area of 220 square meters, that seems fairly big. Suppose it's, I don't know, 4 inches or so thick. That's fairly thick, but okay. That's easy because it's about 10 centimeters, so about 0.1 meters. So that would have a volume of 220 cubic meters. If we say it's made out of something about the density of wood, say it's a density of, I don't know, 800 or 900, let's say, kilograms per meters cubed. I just want to estimate how this force compares to the weight of this roof. Is it going to just, if it's not nailed down, is it going to just lift up due to the pressure difference? Forget the fact that the wind might be going under the eaves and prying it up. So if we do that, we can find the mass. When I calculate that, I get a mass of about 198 times 10 to the third kilograms, which is pretty big, multiplied by another 10 by g, and so m times g gives me about 2 times 10 to the 6 newtons. So 2 times 10 to the 6 newtons, and I've got an upward force that's 2 times 10 to the 5th newtons. It's not going to just pick up the roof. Now, can it pull up shingles? Absolutely. But the issue is that you can also have fairly light roofs, like tin roofs, can be picked up with this kind of force.